So now we're going to explore forces in 2-dimension versus 1. And it makes it a little bit more complicated, but in reality it's not that bad. We're going to treat it exactly the same as we did with kinematics. In kinematics, remember, we broke apart a projectile that's going off an angle into its x components and its y components. That's the only way we could compare it, right? If it's at an angle, they're not going to affect each other the same way. So we're going to do the same thing with forces. We're going to break it up into its x component and its y component, and that way we could actually add them together when they're in the same axis. So when you look here, it looks kind of confusing, but we're going to break it apart into its I guess fundaments or its components, so it's much easier to compare. And the goal is to kind of explain what's going to happen when something is on a slope. So a lot of times you're going to design, let's say, a road, and you need to make sure that it is perfectly banked, or a racetrack, or even things that are on an angle, how it's going to react to things. So that's kind of what we're going to explore today, the classic kind of slope friction kind of problems. Initially, what I want to show here is that you have an object, and I have two pictures because I'm going to zoom in on one. And we want to talk about frame of reference. What is easier to kind of mentally figure out what's going on? Before we move on, I do want to explain, okay, which component do we want to break it down into? Here we have two forces. We have force normal, and then we have force of gravity. Right now, they're not in the same plane. So in the force normal one, its x is this way and its y is this way. And for the gravity, its x is this way and its y is this way. So you'll notice that the axes are different. So we're going to pick one and we're going to rotate it so that it's on the same axis as the other one. Then it's much easier to compare its x and its y. Which one do we pick? One answer is better than another. You could pick either one, but there's a reason why one answer is better than the other, and I'm going to try to show you once we include friction. So if we include friction, let me label all the forces that are here. You have force normal, and let me do it over here so it's much easier to see what's going on. So I'm going to do it without the picture, but the picture's there. So here's here's the ground, here's the slope. You have force normal, which is this way. You have force of friction, which is parallel to the surface. Here's force friction. And then you have force of gravity, which is this way. And then you have one last one, which technically isn't a force, but it's important. We're going to call it DOM, or direction of motion. Okay, so when you look here, you have 1, 2, 3-ish things in the same plane. And what I mean by same plane is that here is its y, here is its x. So these are very easy to kind of work together because they're either on the x or y. Gravity is at an angle, so that makes it harder. So it makes much more sense just to change gravity into its components, F, G, X, and I got to mix up FGY and FGX. Because here we only have to do it once. If we did it with Fn, we're going to break it up into its components and break this one into its components. Now, once it's broken up to components, now we could compare force of friction and force of gravity and x friction because they're in the same axis, and we could compare force normal with FGY. So that's the goal, to kind of break it up into components so you can compare these things together, or actually make a relationship of the two. Now, another way of looking at it is what do we do with our frame of reference? So for me, I'm okay working at angles, but for some people, it's easier to rotate this around. So it might be easier to mentally kind of rotate the surface around a little bit like that. So now when we look at it, let me go back to my presentation. Now when you look at it, you can see that here, now this is my x and y. And it makes more sense because this is the true x and this is the true y. Okay. Here you have to have a mental kind of, I wouldn't say ability, but you just have to mentally see that this is my x-axis and this is my y-axis, even though it's at a slant. So do whichever way works for you. Whether it's to rotate, it's kind of weird now that we're at home, but in class I would just say just rotate your paper and work on the side. but now you kind of have to, I guess, rotate your picture, or when you're drawing it, you could draw it kind of sideways. So whatever works best for you, that's perfectly fine for the case. Now, I do want to talk about how we derived this FGX mg cosine theta. So let me kind of get rid of certain things so we could kind of start from there. Okay, so where did this come from? So you'll notice here, I'm going to draw another right triangle to kind of do a reference. Here you have the following, and even though the center of mass is right here, it's a little bit harder to work up here versus down here. So I'm going to redraw it with this down here. Let me get rid of one thing so I have more room to work with. So I'm going to get rid of this picture for now. Kind of just move it off to the side. Okay, so I'm going to redraw in a way that it might be a little bit more clear. So here's my slope. Okay, we know this is the angle right here. We're going to draw a couple forces here already. So force normal is this way. We're going to imagine the object right here. I just want to get rid of it so it's much easier to see all these vectors. And then you have force of gravity right here. Like I said before, I want to make sure that they're in the same x and y direction. So I'm going to change one. If I extend this out here to here, what you're going to notice is I have a right angle here, and then I also have a right angle here. FG is perpendicular to the ground. FN is perpendicular to the surface. Okay, when this is the case, we're going to create a right triangle, and we're going to actually have some components that we could find useful for us. So the thing that we want to do is eventually do this right here with this FGX, and then here, XGY, and then here, which is FGY. What we have here is FG. That was a really bad color, so let me kind of redo it again. Oh, yes. Okay, there we go. What I have here are two colors. I'm going to change this into my FG in the Y, and then FG and the X. So remember, we're breaking down a vector into its components in the X and Y, and then notice now I could compare FN and FG in the Y direction, and now FGX is in the same direction of my motion. So that's our goal. We want to find a value for this. So what we have here is an angle right here, and we have here, and then we have another 90-degree right here. So we're going to create two right triangles, and we want to figure out, okay, how is this angle somehow related to this one over here? And it's actually not that bad. So here you have a 90 degrees, so that means this one is 90 minus theta right here. Here you'll notice is another 90 degree. So if this is also 90 minus theta from here, so these technically are the same angles. So when you look at the reference, this angle right here is the same angle as here. Once that's true, and we're just looking at it a little bit rotated, here is my hypotenuse. Here's one leg, here's another leg. So if we have sine of theta, which is opposite over hypotenuse, and the opposite will be this one right here, which we'll label FGX, will be FGX over the hypotenuse, which will be FG. And then when you move it around, FG sine theta is going to be equal to FG in the x direction. And then if we do the same thing with cosine, cosine theta will be this one right here, FG in the y direction over hypotenuse, which is FG. So you multiply across, so FG cosine theta equals FG in the y direction. So here's my two things which will hold true, because even if the slope is rotated on the other side, the angle is still going to be the same. Your x and y direction is still going to be in the same height, I guess, leg wise. So FGY will always be FG cosine theta, and then FGX will always be sine theta. So you'll notice that's where we get these. So that's how you kind of derive it based on the triangle itself. Now, when we want to solve a problem, we do it the same way that we did it before. What we want to do is ask ourselves, if we're trying to find A, what are all the forces in the y direction, what are all forces in the x direction, and figure out what's going on. Without friction, all we have to worry about is force of gravity in x, and then we just have summation, and x is equal to ma. With friction, then we just need to involve friction. So you're going to have to do static first, and then ask yourself whether it's going to move. If it's going to move, then it's going to be using kinetic friction. If it doesn't move, you're done. A is equal to 0. So that's kind of the process that you have there. So if we do a couple problems really quickly, without friction, let's just make up some things. So here is my slope. And here's my ground. Let's say it's 30 degrees. Here's my object. And let's say it has a mass of 1 kilogram. So we want to know what is the acceleration if there was no friction. Okay. We have two forces here that's acting on it, Fg and Fn. Unfortunately, you don't know what Fn is. In this case, we really don't need to know. Okay. We just need to know what Fg is. Fg in this case is negative 10 newtons. Unfortunately, it is this way. So it's doing two things here. There's one force of friction here, Fg in the y, and another one this way, Fgx. Now, if there was friction, this is important because you need it to solve for friction, right? Fgy is the same as Fg or Fn, which you need for friction. In this case, we don't need it. The only thing that we're worried about here is Fg in the x direction, because that's the direction of motion. So here, we have force of gravity in the x. So now technically this thing has, if we redraw it, three things acting on it. Force normal, which is surface, Fg in the y direction, and Fg in the x direction. So these are the three forces. We could ignore y because we're not doing friction. The only thing that's important is Fgx. So sum of all forces in the x direction is just equal to Fgx. We're going to make this equal to ma, so we can solve for a. Fgx, if you look back, was mg sine theta. Mass here is 1 kilogram, and we're looking for a. So mass is still 1. Gravity, we're going to use 10 just to make life easier. Sine of 30 is equal to 1a. So the 1 kind of could disappear. And then this will come in play later. Notice that the m does cancel out. And you're just left with 10 sine 30 equals a. And that's it. Just plug it into your calculator. Make sure you're in radians. Or sorry, degrees and not radians. And you should get the right answer. I believe sine of 30 is 0.5. But I'm just going to make sure because my mental math has declined over the years. So acceleration here is 0.5 times 10 or 5 meters per second squared. Now, technically, it's negative because it's going to the left. It depends how you want to define sine. Because things are at an angle, it's going to be a little bit differently. So you could just say 5 meters per second down the slope is probably the easiest way of explaining it without getting into technical term. But you could say like to the left at 30 degrees. At an angle, you kind of just have to mentally describe what's going on versus just using plus or minus. Now, what happens if there was friction? So we'll kind of do the same thing, and let me erase a couple of things. So we still want to find A. I'm going to erase this one. Actually, you know what? I could come back to it. Okay, let me erase all this. And now if we add friction, I want to figure out a couple things. Okay, so if there's friction, we need a mu. So I'm going to add that right here. Let's say this one's with friction, so you have mu. Whoa. You have mu s, which is, I'm going to make it pretty small, 0.2, and let's say mu k is 0.1. Okay, so we want to ask ourselves, will it move? So we want to find out. Okay, so now with friction, you have one more force. Force of friction, but we have no idea what this is. We do know what Fgx was, right? It was 5. I think, was it 5? Oh, no, let me check it really fast. It was sine, it'll be 10 times, so yeah, 5. Okay, so we know Fgx is 5, and we want to know what Ff is. We want to know if it moves, because if force of friction max is bigger than 5, then it's not going to move, but if it's smaller, it is. So the first thing we need to do is figure out what force of friction is, which is, remember, mu Fn. the k right here or the mu right here, depending on what we're doing. First, we're going to do static. Now, we need to know what Fn is. So we're going to have to solve for Fgy to find Fn. So remember, sum of all forces in the y direction is Fg in the y plus force normal. Since it's not moving up or down, it's not moving off the surface, we know it's going to be equal 0. Acceleration there is 0. So Fg in the y is equal to negative Fn. So that's all we have to do. Fgy, remember, is mg cosine theta. And we're not going to worry about sine because I just want a positive number. So here we have 1 times 10 cosine of 30. So this one's not going to be as nice number as before. It'll kind of give us a good range of what's going on. So 10 times cosine of 30 will give us 8.66. And that's force normal. Plug that into here. 0.2 times 8.66 will give us force of friction static max 1.73 newtons. So here, this one is smaller than gravity, so it's going to move. So once it's moved, we're going to now use, yes, it moves. Now we're going to use mu k. Same thing, divided by 2 because it's just half. So force of friction kinetic is equal to 0.866 newtons. And we're just going to do sum of all forces in that direction. So here we're going to add one more force, force of kinetic friction. And we want to find the sum of all forces in the x direction. So you have Fgx plus Fkf, or Fk, is equal to ma. This one was 5 minus this one, which is 0.866. Sign-wise, they just need to be opposite. You can make gravity negative and this one positive because technically this one's going to the right. It doesn't really matter. Like I said, it's at an angle now, so it matters only that they're opposite. Equal to 1 times a. So minus 5 for me on my calculator. So I get acceleration of 4.13. Now, remember, this is down the slope. So whatever sign it is that you have for downslope it is. So it's slowed down a little because of kinetic friction, but there it is. So is at an angle harder? Not really, but it's different. You're going to have to take a little bit of time breaking it apart, but it's still there. The same process as before. That's what I'm trying to say.